Hello everyone. Well, in this class, we'll start discussing a little bit about what are the types of sensors and actuators, and also we will discuss what is a sensor and actuator that can be used as an input or an output into a PLC. Okay, so you remember that well in previous classes I introduced the idea of the PLC, and basically. Uh, the idea here is that, well, you have the structure of the PLC has the inputs. No, you have here the inputs. You have the PLC that contains a CPU, and the PLC, based on these inputs, can activate or turn off an output. Okay? So this is the general structure of the PLC, and also we mentioned that, well, you can have inputs like switches or sensors. Okay? And the outputs can be relay coils and the motors. Okay, so the idea of this class is that we discuss more deeply what are these things, no? What are the inputs, what are the outputs, what type of sensors you can use, what is a sensor, what is an actuator, and what type of actuators you can control through the PLC. Okay, so well, in order to do that, I prepared some presentation. So let's continue. So, well, regarding the sensors and actuators, well, we have the following points. Okay, the sensor basically refers to a device that responds to a physical stimulus. And based on that physical stimulus, it produces an electrical signal. Okay? For example, we have temperature, pressure, flow, and vibration sensors. And all these sensors, what they have in common is that they respond to this physical quantity, a temperature change, a pressure change, or a flow change in a fluid, or a vibration. They have a vibration response that produces an electrical signal in response to these physical quantities. Okay, so one of the sensors that we already discussed many times are the switches. Okay, and as we mentioned previously, you can have a normally open switch or a normally closed switch. Okay, we also call switches contacts. Okay, and well, you can connect the switch in different configurations. For example, here we have a normally open switch, no? And here the switch is connected into one of its terminals to a voltage, and in the other terminal is connected directly to the input of the PLC. But also we have the following configuration, like in the right, in which you have the voltage of the power supply that is connected directly to the input of the PLC, and the other terminal of the switch. No, here we have the switch, but the other terminal, this one, is connected to the ground terminal of the circuit. So when you close the switch, the current, instead of going to the PLC, will go to the ground terminal. Okay? So this is like different ways in which you can connect the switch. And also they will behave differently and into the way in which they provide an input into the PLC. For example, here the PLC is always receiving a high voltage. Okay. No, for instance, we can have here, let me erase this. We can have here the voltage, no, the power supply always connected. But when you close the switch, the voltage will go directly to the reference terminal, no? Or more precisely, the current of the circuit will go into this direction, okay? And here, for example, in the left side, you can see that the input of the PLC is not connected to anything. Until you close the switch, the input is connected directly to the input of, well, the input is connected directly to the power supply, okay, when you close the switch. Okay, so there are different behaviors there, but you don't need to worry too much about right now these aspects. The main idea is, well, you have this switch. This is a type of sensors that you can use in the PLC. And well, based on these configurations, you can connect the switch into the PLC. Okay. Another type of switch is called the limit switches. Okay. Basically, limit switches have a lever, for example, or a roller. And this lever or roller basically are mechanical um, actuation mechanisms that when you move this lever or you move this roller, these devices are connected through an electrical circuit. So depending on how this lever is moved or this roller is moved, you can open or close a switch. Okay. So that's why we have here this aspect, no? There is a mechanical link to an electric circuit, no? And this electric circuit is essentially a switch, okay? And limit switches are mainly used when you want to detect the presence or the passage of a moving part. Okay, for instance, you have a transportation band, no? And you want to detect when an object passes through the transportation band, okay? Or you want to detect when the transportation band is moving an object, okay? So these are the limit switches. In fact, the most important part is that these limit switches can detect moving objects, okay? And they can detect these moving objects through the lever or roller, that is a mechanical system that is linked to an electrical circuit. Okay, so here, for example, I wanted to show you some parts of a video in which they are showing no different types of limit switches. You can have, for instance, a whisker as a mechanism. You can have a roller, and you can have a lever or a plunger. But regardless of the mechanisms that you have, all these mechanisms are connected to an electric circuit. Okay, so you can close or open a contact based on the activation or movement of this whisker, roller, or lever. Okay, so this is like an example, no? You have here a limit switch with a roller, and when this box is moving, the roller will also move. But the movement of this roller will produce that a contact can be closed or open. And in this way, we can detect the presence of a moving object. Okay? So, well, this is another example. We have here another type of roller. This is basically detecting how this gray part is moving around this transportation band. Okay, and well, this is a more detailed diagram of the limit switch. You can see here that we have the roller, no, or the mechanism, and this is linked to a contact. So if you move this roller, you can close or open this contact. Okay, well, this is another example, I think, of how the limit switch is working. Now, here, for instance, you can see that the roller has moved, and this is closing the switch, no, when the moving is passing through the roller. Okay, and well, these are the symbols that you can have. You don't need to memorize this. I am only showing them very quickly. And well, you can have different configurations, etc. But I think that one of the important parts of switches or mechanical switches is that they require a physical contact with the object in order to detect its presence, okay, or in order to close or open a switch. But there are other type of sensors that are called proximity sensors that do not require a contact with the object, okay? So we will discuss that, in fact, in the following slide. For instance, regarding proximity sensors, we can have inductive, capacitive, magnetic, ultrasonic sensors. In particular, inductive sensors can detect only metallic objects. Capacitive sensors can detect any type of material, not only non-metallic objects. They can detect metals, they can detect any type of material, okay? Magnetic sensors can only detect magnets, and ultrasonic sensors are a particular case because these three in particular can only detect the presence or the absence of an object. But the ultrasonic sensor has the capability of and not only detecting the presence of an object, but also measuring the distance, no, between the object and the sensor. Okay, so here is like a small video that more or less illustrates this behavior. So essentially, for example, they have here a setup, no, that is basically a transportation band that is used to move these containers, and these containers are filled with a liquid. Okay, so you can use, um, for instance, a capacitive sensor to detect and well how the liquid is filling, no, in the container, or how the container is filled with a liquid, and you can detect the presence of the cover in the container. And in this case, they are using a metallic cover in order to detect that in order to see if the container is closed, no, with the metallic cover. And for this purpose, they are using an inductive sensor. Okay, this diagram basically is telling you that, for instance, for an inductive sensor, you can have different, well, you can detect different types of metals. There is certain sensitivity because you require a lower distance to detect different types of metals. For instance, you require a closer distance to the sensor when you want to detect copper compared to ferrous metals. Okay. So this is basically explaining how the connections of the inductive sensors work. You always have three terminals. One is the voltage source, and the middle one is the signal, or the electrical signal that is produced by the presence or the absence of the metallic object. Okay. Another thing is that, well, these sensors can be shielded. No, that means that they have a cover, or they can be unshielded. That means that they don't have a cover at the top. Okay. So depending on this cover, or the presence of this cover or not, well, you have a particular detection scope. No, you will have a greater aperture or a lower aperture. This is clearly explained by the following diagram, where you can see that if you have a shielded sensor, the scope, no, or the range in which the vision of the sensor is more concentrated in the shielded version compared to the unshielded sensor, where you have a greater scope, no, for detecting the object. Now, well, this is different ways in which you can connect the sensor as a normally open or normally closed contact. Because remember that these sensors can only detect the presence or absence of an object. So you will have here different connections in which you can connect these sensors in order to reproduce the behavior of a normally open or normally closed contact. Um, and well, we have a similar behavior for the capacitive sensor. In fact, the structure is very similar. Just remember that the capacitive sensor can only detect, can detect any material. And well, you have like different configurations. Here they are explaining that capacitive sensors are mainly used to detect the level of a liquid in a container, like in this example. So for instance, when this bottle or this container is filled with this liquid, the capacitive sensor uh, can detect that. Okay, here they are showing in greater detail how the inductive sensor is working. In particular, it is detecting the cover of this container that is right here. That is a metallic cover for the container. So they are using these sensors to detect the presence of these objects in the container. And I think that, well, here they are basically showing you the different types of connections that you need to make in order to configure the capacitive sensor as a normally open and normally closed contact. And well, here it is showing basically a summary of the differences between inductive and capacitive sensors. Okay. So another example of a proximity sensor are ultrasonic sensors. And basically these type of sensors are based on the principle of how quickly the sound is traveling through the space. So we know that, before that, we know that the ultrasonic sensor has the following structure. We have a transmitter, and this transmitter basically is producing a sound, okay? And that sound is traveling from the transmitter of the ultrasonic sensor to an object, okay? But this sound goes to the object and then is bounced back to the sensor, okay? And this sound is received by another component that is also called the receiver. So basically, the idea of the ultrasonic sensor is that, well, we can produce a sound and we can measure how this sound is traveling through the space, okay? So this sound will travel, no, will go to the object, then it will bounce back to the sensor, and the sensor will travel from the object to the sensor, no? First, it goes from the sensor to the object, and then it goes from the object to the sensor. So we can measure the time it takes the sound to travel from the sensor to the object and then going back, okay? So we can use this relationship, no, that is basically the distance from the sensor to the object is equal to the time it takes the sound from traveling from the sensor to the object and going back, times the speed of sound, that is invariant. We know the speed of sound, and we need to divide this quantity by 2. And the reason that we need to divide this quantity by 2 is that, well, remember that here we are measuring the time it takes from the sound from going from the transmitter to the object, and then we need to measure the time that it goes from the object to the receiver. So we have like the double time. So that's why we need to divide this quantity by 2 in order to have the exact distance, because if we do not divide this by 2, we will counting a double distance because we are measuring the time it takes from the sound, from going from the sensor to the object, and then going from the object to the receiver. Okay? So here I place like comparison between the different types of proximity sensors. I think that this is essentially summarizing all the parts of the ultrasonic sensors for the proximity sensors. So basically, the main difference is that the type of material they can detect, the range, that, for example, inductive, magnetic, and capacitive sensors have a very low detection range. But on the other hand, ultrasonic sensors have a greater detection range. But also they are more costly compared to the other types of sensors. For instance, also they can have certain insensitivity to disturbances. For instance, ultrasonic sensors are susceptible to airflow, capacitive sensors are susceptible to humidity and vapors, magnetic sensors are susceptible to other magnetic fields, and inductive sensors do not have any sensitivity. Okay, so I think that the main idea is that rather than memorizing all the connections of a proximity sensor, is that you know which type of materials they can detect, their detection range, and also the costs and benefits of using one sensor over another. Okay, also it depends mainly on the application that you want to develop with the development, with the selection of a sensor or or the absence of a sensor, no? So another element that I wanted to discuss here is the output devices that are basically the actuators. So the output ports of the PLC are often of the relay type. A relay is basically a solenoid or a coil that allows us to control electrically different types of electromechanical systems. Okay? So basically, this output channel of the PLC is used to control actuators, no? And these actuators can be controlled to this relay in order to control some process. And the term actuator basically refers to a device that can produce a torque, a force, or a displacement when it is stimulated with an electrical, pneumatic, or hydraulic input. Okay, so for example, one of the common types of inputs are the relay. Relays, also called solenoids, are in fact the basis of many control outputs. And well, this is like the electrical diagram of the relay. Here you have a voltage. According to this diagram, you will have in this part an input voltage that goes from 0 to 5 volts. This will come from the PLC. No, this is the output or the activation that the PLC is sending or generating. And we are connecting this output of the PLC to the relay. The relay is essentially a coil. What the interesting part is that when you connect a positive voltage into these two terminals, a current will be generated. And this current, when it travels through this coil or this solenoid, will produce a magnetic field. So the activation of the or the presence of this magnetic field will control the switch. No, for instance, if we have a magnetic field, we can close the switch. But if I place a voltage equal to 0 volts, for example, the switch will be open. Okay. So depending on the level of voltage that you apply to this region of the relay, you can activate or deactivate or open or close a switch based on the magnetic field that is generated by this coil. But the advantage of this is that, for instance, you can control a a high power rating system. For example, you can connect here a motor, okay, and that maybe operates at a voltage of, I don't know, 120 volts, for example, and you can control this type of device that requires a higher voltage with a low power system, that is the PLC, that according to this diagram only works on at most at 5 volts. Okay, so the interesting part is that, well, you can have a low power system in this region and control a high power system. But these two systems are separated because they are not physically connected. Basically, we are switching these contacts based on a magnetic field, but not a direct connections or contact between the two elements. So for example, if you have here a short circuit where the motor is connected, well, this short circuit will not affect the PLC electronics because they are not physically connected. Okay, so that is very useful because in case this circuit is damaged or the motor is damaged, well, the damage on that circuit will not affect the electronics of the PLC because they are not physically connected between them. Okay, so this is like one type of actuator that you can use. In fact, the relays can be used for controlling motors or directional control valves. Okay, so well, another type of actuator that we can control are these things that are called the directional control valves. They can be operated through relays or solenoids. And basically, directional control valves allow us to control the direction of a fluid inside them. And this fluid can be air or oil. But based on the pressure generated by these fluids, we can control, for example, pistons, no? That can be automating certain manufacturing process. So, for example, here we have a small video of the application of a directional control valve. This is like a schematic of a directional control valve. So basically, this directional control valve can be used to control, for instance, this aperture. Okay, we have here a piston, and this piston is open and closing um, this aperture of this manufacturing system. No, I think that this is a soil. So for instance, you can close or open this aperture with a piston that is connected through a directional control valve. Here we are controlling the flow of air inside the piston. And based on the presence or absence of air within this piston or cylinder, we can open and close this aperture, no? So this is like a better illustration of what is happening. Here you can see that we have a piston, and the direction control valve can allow us to push air into this region in order to extend a cylinder, and in this case, close this aperture. But when you exhaust air in this region and input air in this part with the help of the directional control valve, you can retract the piston and in this case open this aperture. Okay, so that is one of the main applications that we have related to directional control valves, because we can control the extension or retraction of a piston that is basically controlling the aperture of this hole, and based on that, we can control this process, okay? But here we are using a fluid, that in this case is the air, in order to control how the air is exiting or entering the cavities of the cylinder or the piston in order to extend or retract the system. Okay, and well, here you can see that we have some cables. Basically, this means that the flow of air that is controlled with the directional control valve is controlled electrically with a relay or solenoid. And this relay or solenoid that is right here is controlled by the PLC output. And finally, one of the other types of actuators that you can use are electric motors. Basically, electric motors can be divided into elements or two main categories. We have a DC or AC motors. And the most common ones are the more efficient are the AC motors. They are widely used in industry, or for instance, for moving a transportation van. And well, here I place some of the examples of electric motors that you can encounter. In fact, many of them, for instance, the shunt motor, the compound motor, the brushless motor, and the stepper motors are a type of DC motor. But on the other hand, induction and synchronous motors are a type of AC motors. Okay, so yeah, well, I think that the most important part to understand about electric motors is that they are basically converting electrical energy into electricity. Okay, so we can control these devices by generating an electrical signal from the PLC. And based on the activation of that electrical signal, we can make the motor to start turning, no? Or to start rotating its shaft in order to produce certain movement in the system. So I think that, well, this is like a quick overview of the type of actuators and sensors that you can encounter for a PLC. Later, we will discuss pneumatic circuits. So this will be all for this video. I hope you like it and see you later.